there we go. I think we should be live now. So folks, I was saying that last time we covered section. We essentially finished section 5.1, the areas between curves. But the problems that we did here are problems that used some pictures from the book. Most of them. We did one that didn't have a picture, but it was fairly easy to picture with decimals. All of these are easy to picture with decimals. I'm not saying that they're difficult, but there's going to be problems in your book where you don't have a picture and you have to figure out the picture. So my suggestion is that you all familiarize yourself with decimals so you can actually figure out these pictures, because some aspects of the pictures are very important and actually key in some cases. You won't be able to find the bounds for integration if you don't know how to figure out the picture. So please make sure that you understand what's going on here. All right. And somebody else just joined. Okay, that's fine. So let us go ahead now and let us take a look at a problem that does not come with a picture. And let's see how to do this particular problem. And I'm going to do number 30. So I'm going to do a couple of problems that do not have picture. We'll graph them and we'll figure out what the picture is. 2 or 3 problems, right? So depending on how much time we have, because I also plan today, folks, to give you a short introduction to volumes. Very easy topics. You will see it's going to be a breeze. We'll do one of those, just a theoretical discussion. All right, so right now I am going to, one second, let me pull some things up here. All right, so I'm going to discuss problem 13, folks, of section 5.1. Now this problem is the following. So you're looking at, so again, they don't give you any picture, they just tell you, y equals 12 minus x squared, and then the other one is y equals x squared minus 6. So these are the curves that cut out my domain. What do we do with these two? Well, we want to find the area between them. So it says here, find the area between them. Now, if I knew some sort of a picture, if I knew what the graphs of these look like, and you can actually find them, it's not terribly difficult, then you would easily set up the integral, because all you have to do is to set up the bounds, right? The bounds, and if you know the bounds, then just say the top part minus the bottom part. But even if you don't know that, which one is the top and the bottom, you can just subtract them randomly, and maybe at the end you might have to adjust the minus sign. So that's kind of the only problem with that. So it's not difficult. The only thing is to figure out those bounds, and those bounds are figured out based on a picture. So what I'm going to do, folks, I'm going to pull decimals, and I'll pull it on your screen as well here. So let's pull decimals here on the screen. There we go. There's my decimals. And I'm working in decimals right now, the graphing calculator. And I have the curves. So the curves are, for this problem, y equals 12 minus x squared. All right, there's one of them. So let's make them kind of smaller like that so we can actually see them. And the second one is in problem 13, y equals x squared minus 6. All right, folks, so you can see what I'm talking about. So we're talking about the area between these, so this kind of egg-shaped, area here. That's the area that we want to evaluate. And very important for this particular area that I put on the screen here is the intersection points. Now you can see, folks, that, that this area goes from, so the leftmost point, the left corner is this one, negative 3, 3, and the right corner is 3, comma 3. So this is the way we set up the integral. These are going to be negative 3 and 3 are going to be the bounds for my integral. So now if I want to calculate, I also see another thing that's useful to us is that the red curve is the top part. So this one here, so that's the top part, and that has equation 12 minus x squared. So I know that the first one is the top part. The blue curve, this one here, oops, saying the blue curve is the bottom part. So you can see that the bottom part of this equation is given by the blue curve, which is x squared minus 6. So, so this thing here is equal to, and 1 second, what is that thing? All right, so I'm going to calculate the integral again. Remember, the area is, and it's very easy, again, an integral from negative 3 to 3, and then the top equation, 12 minus x squared, minus, and the bottom equation is, oops, sorry about that, x squared minus 6 dx. So this is going to be the area between the two curves. Now this area here is a very simple integral. In fact, you can, if you want, start by simplifying a little bit here. So negative 3 to 3. Let's say. I don't know, so negative x squared minus another x squared is negative 2x squared. Collect the like powers, folks. And then there's 12 minus negative 6, which would be plus 18. That's going to be that dx. Now, if you don't want to calculate this with an antiderivative, I'm going to calculate this with an antiderivative. But if you don't want to, you could have easily calculated this particular integral with decimals. So I'm going to calculate this with an antiderivative, as I said. But first of all, let's do that quickly with decimals to see how easy it is to do this problem with decimals. So we're going to go back to our friend decimals, and we're going to say here, hey, since you helped me figure out these things, why don't you help me figure out how to calculate the integral? And that's going to be easy. INT for the integral sign from negative 3 over here, up arrow to 3. And remember when you write things here, see it kind of pops up and down there. You want to put everything in between parentheses and then say dx. And what I'm going to do, I'm going to say 12 minus x squared. Oops. That's not what I wanted. 12 minus x squared, like that. Minus, so that's the top curve, minus, and then x squared minus 6, the bottom part. So this is the integral, and there we go. So it spits out the answer immediately, 72. All right, so let's calculate this like, we do. So this is with technology. There's nothing wrong with doing that with technology. In fact, I'll allow you to do this with technology on tests. However, there will be cases when I'm going to ask, show your steps when you evaluate the integral. In those cases, please do show the steps like I will show here on the whiteboard in a minute, in a second. So we're going to start calculating this integral here. That's the one that we evaluate because it's the simplified version of that. So we're going to look at the integral. So we evaluate negative 2x squared plus 18 dx. This is, folks, an antiderivative, and it's as easy as saying, well, the antiderivative of negative 2x squared is negative 2/3 x cubed, and the antiderivative of 18 is 18x. Right? This is the antiderivative, this guy. And that's what I'm going to use to evaluate my integral here, my definite integral. So that's going to the definite integral, and I'm going to write it here. So so it's this one here. So let me just delete that thing. 1 second, folks. So let's put the red. Oops, doesn't let me. Okay. So draw. All right, about that. 1 second. It doesn't let me. Doesn't get off. Okay, there we go. So so let's do that here. The calculation. I did that with red. So let's. So we're gonna say, you know what? It's negative 2/3, and again I'm substituting 3 times 3 cubed minus plus 18 times 3, just that for this part, minus, and then we're going to do minus negative 2/3 times negative 3 cubed plus 18 times negative 3. So this is going to be the calculation here, and that's going to end up being negative 2/3 times 3 cubed is gonna, well, the 3 will simplify out, and if you if you write this out, it's gonna be negative 2 times 3 squared, so that's negative 18 plus 18 times 3 minus, and the next thing here is going to be another positive, so so it's minus minus, it's plus minus, but there's a minus here, so it's going to be minus eventually. Let's see, 18, and then plus plus, because it's minus times this one, minus here, plus 18 times 3. So altogether, this is going to be probably, let's see, so it's 18 times 6 minus 2 18s, it's 18 times 4, it's going to be, yes, 72. There we go. So so the answer here is going to end up being 72. All right, folks. So this is how you would calculate the integral. By the way, the red line here is the fundamental theorem of calculus, right? So you substitute the values, the bounds in the antiderivative. So so I hope everybody remembers that. So that's the thing we're gonna focus on. All right, and as you can see, it's very easy to do these problems with technology. That's what my main battle here is, to convince you that these are not hard problems. When you see a problem like this, it's probably going to be the easier problem of a test. Now I'm gonna do yet another problem in the same spirit. Again, the main battle for these problems is to put your hands on these numbers, on 3 and negative 3, and those are collected by looking at the corners of your picture. Number 14, that's going to be our next problem. Like I usually say, stop the video if you watch it at home. See the statement of the problem. Over here we have y equals x squared and y equals 4x minus x squared. All right, stop the video, find the area between, try to find the area between the two curves. So the area between the two curves. Try to find the area on your own. If you don't succeed, look here. So start the video again and see how I do it here. So again, we do have to figure out what the corners of this picture are, and for that I am going to look at Desmos again. So I am going to pull Desmos here. Desmos, come on. All right, so we are looking at the following different functions, obviously. Here, cut out all of those. So y equals x squared is one of them. All right, there we go. The other one is y equals 4x minus x squared. 4x minus, oops, y equals 4x minus x squared. All right, so there we go. This is kind of a nifty thing here. So it's just this small part where my mouse moves. So so this part over here, and from here going down this way on this other curve. So these two, the area in between is this small one here. That's what we want to calculate. The important thing is that we have the corners of this picture clearly spelled out, as you can see here, at 0 and at 2. So what am I looking at, folks? I'm looking at the x components of these, right? That on the x-axis, because the integral is dx. Remember that. So what we're going to say here, the calculation, I'm going to say, well, let's write down so people can see that written. The area between the two curves is, and I'm going to write down here an integral int from 0 to 2. Right, this corner here, folks, is 2. Remember? 2, 4, yep. All right, from 0 to 2, and the formula is, which one is on top, by the way? So, so I think it's pretty obvious that the black curve is on top, and the black curve has equation 4x minus x squared. All right, minus x squared. And then that's minus, so let's put that between a pair of parentheses as well. Minus x squared. All right, and that's going to be, the reason why it doesn't calculate is because I didn't put the dx here, but I did, and then there we go, it's 2.666, whatever. So, so this number is 2 and 2/3, or if you want, I think it's going to be 8/3. The calculation. I'm not going to do the calculation, you know, by hand. So by this point in time, you're probably all familiar with the way this goes. So again, the fundamental theorem of calculus, folks, that's a thing that you wanna use here. The thing that I want to point out, so again, not a difficult calculation at all. Some of these questions here could be a little trickier. So I'm going to point out one of them, and then I'll let you kind of, you know, try the remaining problems. So, so then I'm going to do yet another one here. Number 15. You will see number 15 is a bit of a trickier question. So let's take a look at the, let's write it on the board, and then I'll write it here. So, so the area, by the way, the area here was set up for this particular problem. I forgot to write it on the board, but integral from 0 to 2, 4x minus x squared dx, and everybody who has the curiosity can calculate this, and probably it will turn out to be 1/3, like you said there on the screen earlier. So I'm going to do number 15. What did I say, 15? Yeah, number 15 of section 5.1. So this is I usually make a selection of problems, folks, before class, and occasionally I change them at the last minute. But this is you know, these were selected because I thought, you know, they sort of first of all, the first two reinforce the ideas that we discuss here. The last one also reinforces those ideas, but it takes you a step further. So you'll see that you have to do something extra for this problem. So so y equals secant squared x. Now this is not going to be a nice graph. This is going to be a mess. You will see. And the other one is y equals cosine 8 cosine x. Okay. And they tell us here, negative pi over 3 less than or equal to x less than or equal to pi over 3. Now, for this particular problem, if they didn't give us this thing, then we would, you know, not know what to do. Because these graphs have a lot of branches. You know, it's not like you have just one single branch. However, this restriction here for the domain of X is very helpful because it tells me, stay in this small interval. Um, uh, the um, the integral will be calculated, but we have to take a look again at the graph. So let's go back to our friend Desmos and let's see what Desmos says about these functions. So you will see what a mess this is here when you do y equals, so what did we say here is secant squared. Oops, not that. Oh, look at that, folks. So not very happy with this. And which one of them is it? Well, there is another problem here. The problem is we don't even have x expressed in radians. So I told you there's an extra step here. Go here on the graph settings where you see this wrench symbol and click on that. That's going to take you, so take your x-axis and say, let's have that for a step of pi over 3, right? Because it tells us in the problem that we want a step of pi over 3, and that will be in radians. And if we do that, look at that. So it shows us, there we go. What is my pi over 3 here? So it shows us that we really are interested in this area from negative pi over 3 to pi over 3. Now, how would I be able to get just that one part? So I don't have to deal with this mess here, these other u's to the left and to the right of that. Well, in order to do that, you are going to have to say, so you're going to have to use these parentheses, okay, here, and you can say here when x, when negative pi over 3, so I just typeset pi and it pulls pi there, less than or equal to x, less than or equal to pi over 3, colon, use the formula secant squared x, much better. Look at that. So there we go. It cut down all the unnecessary stuff and it presented me with a nice picture over here. So when you do that, and then the next thing is, so what's the other function? See, is a secant squared, yes. The other function is 8 cosine x. We're going to do the exact same thing. We're going to say, you know what? Y equals, if I do 8 cosine x, oops, it's kind of nice, but again, there's too many things here, so I don't like that. And I'm going to say, you know what? So let's say, like we did earlier, so let's say curly braces, and then negative pi over 3, less than or equal 2x, less than or equal pi over 3, and then I'll put colon, and the formula was 8 cosine x. And it so happens that this picture looks very much like the one earlier. This is my beautiful picture here, folks. And this is the area that I want to calculate. So the one on top here is 8 cosine x, the purple thing. And I can easily do this with a calculator. So I can say the integral from, and as we said, the corners, be careful here at the corners, negative pi over 3 and pi over 3 are the corners. So I'm going to say here negative pi over 3. And I'm going to say up here pi over 3. And I'm going to say down here, the function at the top was 8 cosine x minus, and the function at the bottom is secant squared x. All right, and that is dx. And when you calculate this, you get this number, which is, I have no idea what that is. So it's just a number. How would I calculate this by hand? If somebody asked me, can you do this by hand? Yes. So the answer is yes. And I'm going to show you folks how to do this by hand. But again, the important thing is that we were able, with the aid of a picture, we were able to find these corners. These are critical. If you don't find these corners properly, then everything else is ruined. So let's go back to our whiteboard, and let's see how to find those the integral. So we're looking at the integral from negative pi over 3 to pi over 3, and the function to be integrated is 8 cosine x minus secant squared x dx. So this is something that I can evaluate as follows. So the antiderivative, so this is what we need, antiderivative of 8 cosine x minus secant squared x dx is, for 8 cosine x is negative 8 sine x. For negative sine squared, secant squared x is negative tangent x. So these are the antiderivatives, folks. Yeah, so for cosine is negative sine, for secant squared is tangent. This is going to go from x equals negative pi over 3 to x equal to pi over 3, which gives us, one second here, which gives us, folks, oh, I have some room here. So negative 8 sine x minus tangent x. Evaluate these numbers for the integral, by the way, folks, we evaluate here. So we will get negative 8 sine of pi over 3 minus tangent of pi over 3 minus, and then we'll have negative 8 sine of negative pi over 3 minus tangent of negative pi over 3. And guess what? I know what these numbers are. Sine of pi over 3, folks, everybody should remember this. So sine of pi over 3 is going to be square root of 3 over 2. So over here, the number is not very pretty, but it can be worked out. Negative 8 square root of 3 over 2 minus tangent of pi over 3, on the other hand, is something that not many people memorize, is square root of 3. So minus square root of 3, that's one part, minus, and then the next thing is negative 8 times sine of negative pi over 3, which is negative 8 times, so it's going to be positive 8 square root of 3 over 2, minus tangent of negative pi over 3 is plus square root of 3. And that is equal to, folks, it's negative 8. By the way, negative 8 times square root of 3 over 2, negative 4 square root of 3 twice. So it's negative 8 square root of 3. And then there's minus square root of 3 minus another square root of 3 minus 2 square root of 3. So all of that is going to be negative 10 square root of 3. Now, if you multiply negative 10 square root of 3 and you want to check your results, so, I think I did the wrong thing. I started with top, okay, so I started with the wrong top part. So let's see, 8 cosine would be probably at the bottom. Let's take a look again at the picture. So 8 cosine, what is that? Okay, so what's this here? Oh, 8 cosine is the top. Okay, that's interesting. Got this thing here at the bottom, minus secant squared. All right, so let's calculate 10 square root of 3. Okay, SQRT 3. Well, that's not the same answer. So I calculated that incorrectly. Sorry about that, folks. Okay, let's take another look at that. So, okay. 8 cosine x, okay, 8. All right, so we got 8 cosine x here, negative secant squared, which is fine. So let's see, negative 8 sine x, which is the antiderivative of that, oh, there we go. So this is where the problem was. I got the antiderivative wrong. My apologies, folks. Positive. So the antiderivative of cosine is sine. So this is where the problem was. Okay, let's let's delete all of these. And let's behave better here. So let's not make mistakes. Sorry about that. All right, so there we go. Let me write. So this is the antiderivative, 8 sine x minus tangent x. And right now we can say, well, over here, let's substitute over here. So this is the function. So 8 sine of pi over 3 minus tangent of pi over 3 minus, and then there's 8 sine of negative pi over 3 minus tangent of negative pi over 3. So that is equal to, and again, 8 here, 8 square root of 3 over 2 minus tangent of pi over 3 is square root of 3, as we said, minus, and over here we have negative 8 square root of 3 over 2 plus square root of 3. So when we do this calculation, this is 4 square root of 3 plus another one from here. It's going to be 8 square root of 3 minus 2 square root of 3, and that's going to end up being 6 square root of 3. Well, this better be the result. So let's go back and let's check the result. Let's check that 6 square root of 3 is the correct number. I'm going to put 6 here, and there we go. Voila. So 6 square root of 3 is exactly the same number as above. So you can actually calculate this number, but that's not, I mean, it's, oops, what did I do here? So that's not the main issue here. So the main issue is to be able to set up the integral. Apologies, why did that come up? So the issue here is to be able to set up the integral properly, and I believe that you can calculate it one way or the other with a calculator or by hand. If you know how to apply the fundamental theorem of calculus and you look carefully there, and you should be able to calculate this kind of area. All right. So that being said, folks, I am going to stop here with these area calculations. And I am going to move on to one of our last lessons here, the estimation of volumes. So let's go and do volumes next. Section 5.2. All right, and whenever you do volumes, you're asking the question, so what kind of volumes? By the way, it could be anything in space really has a volume, as long as they have a closed shape, you know, they enclose something. So any type of box that's closed, well, it has a volume, right? Your fridge has a volume. I don't know. So a ball has a volume. You know, many things have a volume. So what kind of volumes are we calculating here? Well, here's the deal, folks. This section would technically have to be a calculus-free section. So this is something that is forced upon us here just to give kids who don't take calculus-free the option to actually see volumes before, you know, in case they need it for things like physics or some other things. But of course, with fewer tools, so since we don't have the tools of calculus 3, with fewer tools comes, you know, less possibilities. It's not too bad though. So we can still calculate some volumes, but not too sophisticated ones. The ones that we calculate are volumes of revolution. So these are volumes of revolution, and they are all obtained by taking a function. And I'm going to draw the function with red. So taking a function like that, and the line, the real number line, which is that, and there we go. And that's going to be the y-axis and the x-axis. And for example, spinning this about the x-axis. So if you spin this, sort of arc of a circle above the x-axis, then you will get something like this. So you will get, you will get something that looks like a barrel, right? So you will get this sort of shape here. Let me make that red actually. So this shape here is red. Oops, come on, give me the pen. Okay, so that shape is red. And of course, it's red all over. So there we go. That's my barrel that I obtain with this rotation. All right. So this is the thing whose volume I calculate, and I can calculate the volume of that. So the important thing is to know this function here, y equals f of x, to know something about its equation and the bounds here at a and b, whatever these bounds would be. So we want to know them for sure, so what they are. All right, so that being said, let's calculate the volume of a barrel like that, and let's do the following thing. Now, to calculate the volume, let's look at, when you slice it up, you basically slice it up, perpendicular to, so let's say through the center. So you choose a slice that's perpendicular to the sides, and it goes through the centers of those two sides. So the slice goes through the x-axis. And when you slice it up, you get this kind of thing, which is the graph of our original function. But the important thing is that for each x between a and b, this is a and b. If you choose to slice up the picture, if you choose to slice up now, to chop it with slices that are parallel to the sides, then each of those will be a circle, something like this. So we get a bunch of thin slices like that, and the volume would be adding up the areas of these thin slices. So that's basically the idea of calculating the volume. The problem is that these thin slices, they're not all of the same radius. So these circles of different radii, right? These are all circles, folks. And but we know that they are radii, and to add up some very thin slices is the same as calculating an integral. That's what the integral does. It adds up all those possible things, all those possible values, infinitely many. You can make this more rigorous by cutting out fixed slices, calculating volumes and things like that, but I'm not going to go into that. So just intuitively remember that you're looking at an integral to calculate the volume. You're looking at an integral from a to b, and then you're adding up all these areas of these circles, which are pi times r squared. Now, r, the radius, is f of x squared. The radius is f of x, is the height right above the point x. If this is x, then this is going to be f of x, this radius going up, dx. And that, folks, is the formula that we are going to use for volumes of revolution. Very simple formula, very, very simple, folks. You can just calculate any volume of revolution above the x-axis by using this particular formula. So I'm not gonna do an example right now, or well, let me do an example. I'm a little pressed on time, but we still have a little bit here. So let's do a simple example here. So let's do something like this. What happens if you rotate, let's say, this one here? So number three. This is number three of section 5.2. Kind of short on time here, so bear with me for another 4 minutes. Y equals square root of x minus 1, y equals 0, and x equals 5. So we want y equals 0, folks, is the x-axis. This function, square root of x minus 1, goes through this, it looks something like this. So it really starts at 1, y equals square root of x minus 1, and we want that to end up here at 5, where the value is square root of 5 minus 1, or 4. So this is 5 comma 2. All right, so this is the one that we're gonna spin about the x-axis, and we're gonna get the volume of it by using the formula integral from 1 to 5. See, it's still important to find the vertices, yeah? Pi times, and now f of x is this guy, square root of x minus 1 squared, which turns out to be a really simple thing, integral from 1 to 5, pi times x minus 1, simply that, dx. And that goes by setting up the integrals of the antiderivatives. Remember, pi is a constant, so it's going to be pi times 1/2 x squared minus pi x, that's the antiderivative, from x equals 1 to x equals 5. And that goes by substituting the numbers and calculating the answer. So I'm not going to finish up the calculation. This is a routine thing. You can just do that with a calculator if you want. But the point is, this is going to end up being, folks, a multiple of pi. Actually, I can even tell you what that is. So it's 25 over 2, which is 12.5 minus 5. So it's 7.5. All right, minus, and then there's 1 over 2 minus 0.5, so 7 plus pi. So 8 pi is going to be the answer for this particular integral. So the important thing is that this answer is always going to end up, when you rotate things, folks, you'll have pi times something. So that has to do with the fact that you're working with circles. So that's kind of a that's the thing. You're calculating areas of circles, pi r squared, right? This is all for today. So I finished a little hurried here. We'll do more examples like this next time. Again, very easy problems, not to worry about. That's it for today, folks. Thanks for coming to class. All right, let's see. Just close the sharing here, and most important, the